Okay, so yesterday we kind of ended off with this rubber band graph, and I think everybody's kind of got the hang of how to build a graph on Google Sheets. Okay, when we do our lab to do with graphing, I'll run through it all again just so that everyone can build their graph. Okay, the most important part of a graph is the analysis that it allows us to do. Okay, we have to be able to look at a graph and realize what it's telling us. You'd be surprised how uncommon that skill actually is. Okay, because I see it all the time. People put, like, you know, the news puts a graphic up on the TV, and I see people looking at it and going like this. Like, if they look at it upside down, it'll make more sense. Okay, we have to be able to read any type of graph. Okay, all graphs give us virtually the same information. They tell us the trend of two things that are either related to each other or not related to each other. Okay, if I have a graph that looks like this, is there much of a relationship between those two things? No, it's saying that whatever is down here on the x-axis has no effect on whatever's here on the y-axis because it didn't change at all. Okay, if I see a graph that looks like this, okay, that's telling me now that there is a relationship, but it's what? It's linear and it's negative, okay, meaning that as whatever's on the x-axis gets bigger, whatever's on the y-axis gets smaller. As long as this isn't a graph of time and money, you're probably okay. Okay, we don't want that to be time and money, because then as time goes by, you have less and less money. If you didn't get that joke, then that means we need to work on your graphing skills. Okay, so we had to be able to just at a glance see what a graph is telling us and then do further analysis of it. And that's what we were doing with the y equals mx plus b stuff yesterday. Okay, so what we're going to do is look at this graph because we didn't get really a chance to do much with it. Okay, so the graph that we have is showing the length of a rubber band in response to how much force is being applied to it, okay, to stretch it. So when we're looking at the equation here, okay, Google Sheets has told us that y equals 2 times x plus 6.5. Okay, now that means that this equation, remember, sets up like this: y equals m times x plus b. Okay, so y is any y value for any point, x is the x value for that same point, m is the slope, okay, and b is the y-intercept, right, where the line crosses the y-axis. In other words, it's whatever is on the y-axis value at 0, okay? Whenever x is 0, that's what the y value is. So if this is a graph of a rubber band and it's showing force versus length, what does this y-intercept represent? Not so much the constant. Right, it's length when I'm not what? When I'm not stretching it. When the force is 0, the rubber band is 6.5 centimeters in length. Okay, you guys follow me there? Okay, that's some of the more in-depth analysis we have to be able to get from a graph. Sure, we can see that the trend here, just by looking at it, is if I put more force, the rubber band will get longer, to a point, right? Obviously, we didn't get to the point where the rubber band snaps, okay? Because then at that point, I don't know how we would graph that. We wouldn't be able to show it anymore. Okay? It would just, I guess, be a drop-down line to 6.5, okay, or whatever. Okay, that's what we can get from that. Now, let's say that I want to calculate now how much force would be required to make this rubber band 40 centimeters in length. Okay, I want you guys to try that calculation right now. Okay, how much force is needed to stretch the band to 40 centimeters. Okay, give you a minute on that one. Remember that to answer this question, we first have to figure out what's y, what's x, okay, or what values are on the y-axis, what values are on the x-axis, and figure out what you're solving for. Okay, so the first thing I have to figure out is, am I solving for a y value or an x value? I'm solving for an x value. Force is on the x-axis. Okay, so the first thing I'm going to do is manipulate this equation so that it's solving for x. Okay, so in order to do that, okay, I'm going to have y equals 2 times x plus 6.5. All right, what do I do with the 6.5? Subtract it over to the other side. All right, so I got y minus 6.5, and then what do I do with the 2? Divide it over here. All right, so that's going to leave me with x. Now, what's y? 40, right? Okay, I want y to be 40 centimeters. So I'm just going to take y out, and I'm going to plug in 40 for that. Okay, so I got 40 minus 6.5, okay, which is going to be 33.5 divided by 2, okay, 16.5. I'm going to need 16.5 newtons worth of force in order to stretch this rubber band, okay, to 40 centimeters. Right? That's obviously not on the graph, okay, because it's beyond the graph, and that's why we want to have that equation. It allows us to extrapolate, okay, that is, figure stuff out that we didn't actually measure using what we did measure. Okay? All right, let's try this other question here. Let's have you guys tell me how long the rubber band will be if I use 19 newtons worth of force. Okay, so I want you to calculate the length. Whoa, wow, that's supposed to be an H. What the heck am I doing here? Length using 19 newtons. Okay, that's what I want you to calculate now. Length using 19 newtons. Okay, do we have to manipulate the equation for this one? No, we're solving for a y value. We're solving for length. So all we have to do is plug in our numbers. So y will equal 2 times 19 plus 6.5, which should be 44.5, right? Sorry, 44.5 centimeters. Okay, so that's how we use the graphing equation. Now we need to understand the importance of the slope. Okay, what does the slope tell me in this graph? Okay. What are the units for my slope? If I go rise over run, what am I going to get for the units for this slope? Centimeters per Newton. Okay, because I'm going to be dividing, right? If I manipulate y equals mx plus b, okay, for m, it's going to be m equals y minus b over x, which is going to be centimeters minus centimeters, which will stay as centimeters, divided by newtons. Okay, so what I end up with is centimeters per newton. In other words, the slope on this graph tells me how much longer this rubber band gets for every 1 Newton of force that's used. Okay, newtons, by the way, are the units for force. I don't think we covered that, but that's what they are. Okay, newtons are the units for force. So it tells me how much longer the thing will get every Newton of force I increase or decrease by. The base units for newtons are a kilogram meter per second squared. It's mass times acceleration. Okay, you won't need to learn that this year. That's like first part of Unit 2 in Physics 20. All right, so is everyone kind of following me on that one? Okay. Then I'm going to quickly graph this data, so we'll have the graph, and then I'm going to have you calculate a couple of things off of this graph here. So just give me a sec, and I'll have that done. Okay, so now we've got this graph here. Okay, we've got 3 different carts graphed on this graph, and this graph is a graph of position versus time. All right, so what that means is it's telling me where each of the carts is at various points in time. Okay, everyone kind of follow me on that? Okay, so we're actually going to do a lab like this next week where we're going to time some carts as they roll down the atrium, okay, and we'll kind of measure where they are at various, every 5 seconds or so, and then make a graph of that. So it'll look something like this when we do that. Now you'll notice though that on this graph, unlike some of the others we've done, that the points are not perfectly on the lines. Okay, notice how like this red dot right here, okay, is not really on the line. Okay, that's important to realize. Okay, these points are not on the line. In fact, very rarely do points ever end up on a trend line. Okay, unless they're perfectly linear and they all line up like the one we did with the diameter and circumference yesterday. Okay, very rarely does that happen. Okay, so in a lot of cases, the trend line is finding exactly that trend of the points. Okay, it follows their general trend. So a lot of points will be close, but not exactly on. Okay. Now, here's what I want you guys to do. We've got the graphing equations for each cart. Okay, these carts were obviously only timed up until 5 seconds. Now, looking at this graph, which cart was the fastest? Okay, the yellow one. Why do you say the yellow one? It went the furthest away in the shortest amount of time. Okay, like it went 17 meters in 5 seconds, where the others were considerably behind that. All right. If I look at their lines, okay, I also notice that the line for cart 3, the yellow line, is the steepest. All right. So what does that mean that the slope, okay, these slopes represent for this graph? Not acceleration, but close. Speed. Yeah, they represent speed or velocity, because it's just a straight line. They represent the velocity of the object here. And obviously cart 3 was the fastest, so it has the greatest slope. What are the units for that slope? Meters per second. Okay, this is something that we've got to be able to do when we look at a graph. We need to be able to analyze it in such a way that we can look at it and go, okay, this one has the greatest slope. What does the slope represent on this graph? Okay, and I look at it and go, okay, I've got meters, I've got seconds. All right, so the slope would be meters per second. Well, that means the slope is velocity. Okay, that's what we want to do. We don't want to memorize what the slope of every graph we're going to deal with represents. Okay, because while you could get through Science 10 that way, because we only deal with a couple of graphs, you get to Physics 20, we're dealing with 10 or 12 different kinds of graphs. Physics 30, 30 graphs or more. Okay, it becomes impossible to memorize. All right, the slope on a graph of force magnetic versus field strength is acceleration or something like that. Yeah, like I can't even memorize it. I don't bother to memorize it because I look at a graph and analyze each graph separately. Okay, it's easier to do it that way, and I don't have to worry about memorizing something incorrectly. Everyone kind of follow my logic on that? Okay, so on this one here, our fastest cart is cart 3 with a velocity of 3.39 meters per second. Meanwhile, cart 1 only has a velocity of 1.38 meters per second. Now, something else to look at here. When I calculate, if I manipulate y equals mx plus b for slope, right? We already said that m is y minus b over x. What's on the y-axis? Position. Okay, if I go final position minus initial position, what does that calculate? Right, well, displacement technically, but yet if it's a straight line, it's also the distance. All right, so if I go y minus b, okay, that's going to be my final position, whatever y is, and b is my initial position. Okay, so really what I'm doing is going final position minus initial position divided by what's on the x-axis? Time. That's why the velocity is the slope of the line. That's where the velocity formula comes from. Okay, it's the slope of a line on a position time graph. You find that's going to happen a lot. Okay, when we start dealing with velocity versus time graphs, the slope will be acceleration because it'll be the change in velocity divided by the change in time. Okay, most of the formulas we use are just a representation of a linear graph. All right, everyone kind of follow me where that comes from? Okay, we'll talk more about that next week, but I kind of saw that aha moment happen for a few people there, so that's good. Okay. All right, I want you guys to calculate for me how long it will take each cart to reach a position of 100 meters. Okay, so calculate for me using this graph. Calculate how long for each cart to reach a position of 100 meters. Okay. How many people are having trouble with this number? Okay, I kind of thought that. So let's talk about what that number means. Okay, I'm just going to take the graph off here for a second. Okay, if I'm given a number like this, it says 9.52, and then it says like E -3, okay? What they're saying is this is 9.52 times 10 to the power of -3. This is a number in what we call scientific notation. We use scientific notation all the time in physics because we deal in physics with incredibly large numbers and incredibly small numbers. We go everywhere from the mass of a galaxy to the mass of an electron, right? So from really big to incredibly small. We can't represent those numbers as actual numbers, okay? Because the mass of an electron is, what is it, 9.31 times 10 to the, I can't even remember. It's incredibly small. It's really, really tiny, okay? Whereas the mass of a galaxy would be incredibly big. So we represent these numbers by putting them in scientific notation. Scientific notation shows us all the measured values without showing us all the zeros that might be in that number, okay? Because this number, if I expand it out, okay, is 10 to the -3. That means I need to move the decimal to make this number bigger or smaller? Smaller, okay? So I'm going to move it 1, 2, 3 spots. So here's where the decimal is now, and I can expand it out to 0.00952, right? Now, you might think, well, really, couldn't we have just like written those other 2 zeros? Sure, we could have. But if we're dealing with something like the mass of an electron, I don't want to have to write in 20 zeros. It takes too long, okay? Or if I'm, representing Avogadro's number, 6.02 times 10 to the 23, I don't want to write in all those other numbers. It'll take me too long. Okay, so we use scientific notation to represent really big and really small numbers. If I had, let's say, this number, okay, which way do I move the decimal now? To the right. Okay, it's a positive number. Okay, 10 to the 6 is big. All right, so I would move it 6 spots to the right, and then I would have my number. All right, so that's what we're doing when we're doing that. To enter that into your calculator, you enter it in just like you did for Avogadro's number. So that is, okay, I would go in brackets 9.52, and then I'd hit the second function button, get the E there, -3. Right, then I've got it in, and I can work with it from there. Right, so that's what scientific notation is. Okay, so back to calculating how far each, or how long it would take each cart to reach 100 meters. So the 100 meters, X or Y value? It's a Y value, so I'm looking for X, because how long is time, and time is on the X axis. All right, so for cart number 1, if I'm manipulating this for X, I am going to take 100 meters, Y, minus 9.52 times 10 to the -3, okay, minus B, okay, and then divide that by X, okay, or sorry, divide that by M, which is 1.38. Okay, that'll equal X for cart number 1. Okay, so for cart number 1, okay, we're going to have 100, okay, minus 0.00952, okay, divided by 1.38. Why did I do those calculations separately? Why did I get the answer and then divide? Okay, so I do it this way, I get the right answer, which is 72 seconds. If I go 100 minus 0.00952 divided by 1.38, what's my calculator going to do? Right, it's going to do order of operations, and it's going to divide first. Okay. I could put it in brackets, yeah, but I mean, in the end, it's the same thing. I either press enter or I put it in brackets. Okay, I don't get the same number, that's for sure. All right, so the answer there is going to be that it'll take 72 seconds for cart number 1. Okay, for cart number 2, okay, so that's red. Cart number 2, we're going to have 100 minus 0.0524 divided by 2.01. Okay, that'll give us X for cart number 2. So 100 minus 0.0524. Okay, and then divide that by 2.01. All right, so that's going to be quite a bit less time. Okay, 49.7 seconds for that one. And then for cart number 3, okay, I'm going to take 100 and subtract 0.0381 and divide that by 3.39. And only take that one 29 seconds to get to 100 meters. All right. Everybody okay with what we're doing there, Megan? Oh, I totally missed that it was negative. Yes, it does matter. Yes, so I should do that one again. Okay, so we have 100 minus negative, okay, or you could add it, 0.0524. Okay, it's not going to make a huge difference, but I mean, especially with a number that small, but it does make a difference, and we do have to be mindful of that. So I think we had 49 point something seconds before, but yeah, it does make a difference. If that number was any bigger, then yeah, I would have really screwed it up there. All right, any other questions on that one? Okay, so you're not going to be asked to do much more than that in terms of graphing on a unit exam, okay? But expect that on a unit exam, I will put a pre-constructed graph on there and ask you to do exactly this kind of thing. Calculate y when x is this much. Calculate x when y is this much for this particular graph. So you're going to have to be able to manipulate y equals mx plus b and solve for things, okay? All right. Okay. I want you guys to look just at number 4 here. I'm going to make it a bit bigger. Okay, I would like you guys to see if you can determine the slope of each one of the graphs in question number 4. Okay, so you'll have to get a y value. Luckily, these ones, the y values, you can read off of the grid. So we'll do the first one here. We'll do part A together. So if I'm going to calculate the slope of A, okay, I know that the y-intercept, or b, for this graph is 100. Okay, because I can read that right off the graph. Okay, so b equals 100. Okay, and then I just need to pick a point to get y and x from. All right, now there's no points on this graph, but I could use this spot or this spot because it goes right through a grid intersection where I could go over and read the values. All right, so I'll use the last one. Okay, I'll use 304. So y is going to be 300. I think that's supposed to be kilometers. Okay, so we'll say that's kilometers as well. Okay, and x is going to be 4 hours. Okay, can I calculate the slope of that graph now? Right, so I just take y equals m times x plus b, and I solve for m. So m will be y minus b over x. So that'll be 300 minus 100 over 4. 200 over 4 should be 50 kilometers per hour. Okay, everybody follow what I did there? Okay, so I want you guys to do that for B through F, and then we'll walk through them together. Okay, let's have a look at the slopes here for some of these. So if we're looking at B, okay, we've got the time in weeks on the x-axis, and in fact, basically whenever time is a variable, it's going to go on the x-axis. It's always going to be the manipulated variable. Okay, so time in weeks and value of shares in dollars. All right, so we're going to take our m equals, and the y value I'm going to choose will be 20. Okay, so I'm going to take that point right there. So I'll go 20 minus b. B is actually 30. All right, and then I'm going to divide that by x, which is 8. All right, so I've got negative 10 over 8. Okay, which is going to be what, 1.25? All right, so I'm going to get negative $1.25 per week. All right, is this a stock you want to buy? No. Okay. Not yet, anyway. Let it get really low and then see if you think it's going to go up. Then you buy it. Stock market is really like gambling. Okay, but if you know what you're doing, the guys that do this really well will insist it's a science. Okay, not luck, but okay. And some of them do get rich, but some of them get really poor also. Okay, so be mindful of that. Okay, so for graph C here, okay, we've got the mass in kilograms and the time in weeks. Probably the title of this graph would be like I went on a diet, or something like that. Okay, because it's mass in kilograms over time in weeks. All right, so what I'm going to use for that one here, okay, so I'm going to have m, and I'm going to use 50 as my y, 75 is b, okay, divided by x, it's 40 weeks. All right, so they lost negative 25 kilograms in 40 weeks. All right, so we're looking at they're losing negative 0.625 kilograms per week. Whoop, kilograms per week. Okay, which is actually a fairly healthy rate of weight loss. That's about a pound a week. Okay, that's a pretty healthy rate of weight loss. All right. For D here, we've got force in newtons on the y-axis. We've got displacement in meters on the x-axis. We want to find the slope. So again, we'll go m equals, and I'm going to use 20. I'm just going to pick a different one. I'm going to use 20 for y this time. Okay, 20 minus 0. Looks like B is 0 on that one. And that happens for me over 0.4 meters. Okay, would I get the same answer if I used 40 and 0.8 meters? Yeah, I would. That's any point on the graph will work. They're all on the same line. Okay, so 20 over 0.4 should be 50, yeah? I think. So that'll be 50 newtons per meter. No, this one's not cubed. Next one will be cubed. Okay, questions on that one? Xander? Yes. All right, for graph E here, we've got mass in kilograms and volume in meters cubed. Okay, so I'm not sure what this would be a graph of, but okay, it's a graph of kilograms versus meters cubed. Okay, so that one there, M will be 240 minus 0 divided by 3. Okay, so that should be 80. 80 kilograms per cubic meter. Okay. And then for our last one, we got temperature in degrees Celsius versus time in seconds. We're obviously cooling something off in this graph. All right, so M will be 0 minus 30, okay, because B is 30 on this graph, divided by 20 seconds. So that should be 1.5 degrees Celsius per second. Okay. The units, guys, are important. Okay, slope does have to have units. Okay, or I guess it's possible the units could cancel, but most of the time it's going to have units, and we need to make sure we indicate what those are. All right, I think we'll leave it there for today. Okay, we'll be looking at position versus time and velocity versus time graphs on Monday. So it'll be another way of looking at V equals D over T. Okay, but it'll be with graphing.